counts. However, it turned out that's completely wrong. CBA is a technical term in general relativity that will be explained by
Thank you, and thanks for Doug, who like a year ago called me up and said, let's try and help me out to try and get a workshop together. I'm going to try to involve Michael Holtz, David Garfinkel, and a few others. Let's see how it comes out. So one thing we did a few months ago was to say, well, let's just try and schedule the different speakers. I said, well, maybe on the last day you could try and summarize a little bit. And I try from the back taking notes, and I really try. And so this is what TBA means. Because I'm not going to do that. I'll try highlighting a few things, but also hopefully try and make some connection between what some of you guys are doing, what some of us are trying to do, and where there could be potential pathways for better discussion, or at least if some things get done, the other side to be more interested in perhaps utilizing some techniques or attack some problems. So like one side is kind of maybe discretize or whatever. An image of that is this. I mean, you guys are very, very efficient at representing particular features and obstacles. We're more on this side. And after seeing all the baggage that you guys, or machinery that you guys have, I mean, this Lego guy is kind of sad. But if you've ever played with Lego, one of the great things, and this is why this toy is so popular, is that you can do a lot of things. I mean, if this guy is sad, but I can take his head out and then put another one, all of a sudden have a smiley face. So there is one thing that we do try, and I'll try to exemplify why is it that the techniques we use are things that it'll take a while for us to dispense from them, is because it gives us a lot of freedom. And I'll try to explain why and give you examples of things one could do. And if you actually get to show that you can do much better, we're definitely slowly going to try and move beyond the standard techniques we're using. So I'll try in a rather poor way to bring some notes together from I've been hearing kind of from the numerical relativity side, and show you some toy problems, again, that hopefully some of these techniques that you guys are talking might actually help in attacking something. So I'll resonate with several of the talks during the week, and at the same time try and come up with possible toy models to try some of these ideas. So I'll start with talking about things that I think could be relevant if one thinks of the binary black hole problems and the challenges are ahead. We'll go beyond the binary black hole case. We've been hearing a lot about that, but we've heard from Harris things with respect to that have matter, and some of these the reasons we want to go after them. I'll show you some examples, and then think of perhaps new vistas in this context. So let's start with the binary black hole, and I'll tell you what some of the things we're doing and why. So, well, we have heard many times that we cast things in a set of evolution equations and constraints equations. We heard from both Oscar, Fernando, and David, how we work on the analytical side to ensure that they have as nice properties as we can have. And then we press on. We use, I think from your point of view, very outdated things. After all, who wants to use finite differences? These are things from from the time of Newton. Why would we go there? Well, I mean, finite difference is not that it has stagnated in time. They haven't evolved. There is quite a bit of theory behind it. In particular, some of the, I also understood what a complex is after talking with 5 times with different people. Sorry, I'm slow, but I finally understood that. I understood a little bit of the beauty of that and why some structure is required. Well, of course, in a much more rudimentary way, there are things like that in finite differences. So in particular, for instance, you know that in the proving of well-posedness, energy estimates are crucial. There you use summation by parts, and there are operators at the discrete level that satisfy that. And this is how we write our approximation two derivatives. And we can do it to very high orders. And these things are being implemented, are a part of the things that we do every day. With respect to boundary conditions, well, we can kind of distinguish kind of three layers of that problem. Well, with respect to evolution equations, because as Pau said, we can cast things in with respect to series of evolution wave equations, understanding what mode comes in and what mode is going out and how to control those is relatively easy. If we want to make those constraints compatible those conditions or boundary conditions compatible with the constraints, things are more difficult, and Oscar described some of that. But if we also want to make things compatible with the physics of the problem we're trying to solve, we know that's impossible. We do not know, and there is no way to know what are the right boundary conditions in a problem like the binary black hole of the free piece of information that should be coming back from the space of the region of the space-time that we're not evolving, because that is physics of a wave that is going out, backscatter of the potential that comes back in. And if I knew what to put, I would have not solved the problem to begin with. So either one has to take a kind of a winding or longer road to include infinity in the domain, as David described, or even go past that, or perhaps work with a different type of problems, and I'll show you, where the boundary conditions are part of the physics of the problem, and waves are actually bouncing in that boundary and coming back. I'll give you an example of that. Constraints, as you've heard, we deal with typically with constraint dumping. That might involve adding extra parameters, either at the level of the constraint dumping explicitly themselves, or somehow implicitly coming in through the gauge conditions that have been chosen in the combination that, say, is used in the BSSN, as David was stressing. With respect to the initial data, Pablo made a comment on this, so we could do better. He mentioned, for instance, that Kerr black holes are not conformally flat, and this Young radiation has to do with that. And so this would be great to have. Efficiency we achieved through adaptive mesh refinement. And I think it got lost a little bit in the talks that we have options that follow with fixed boxes some particular feature of the solution, but we actually can do better than that, and we're doing better than that in some cases, where the solution or the code is self-aware at the feature of the solution that are coming out dynamically by comparing the solution with a given grid and a finer grid that dynamically in time, and if a particular error tolerance is not satisfied, it keeps refining. And if one is comfortably satisfying that, it de-refines. That's extremely important. So we have feature of the solution in a theory that we don't necessarily yet know, not all is nonlinear content, that has to adapt to something that a priori one doesn't know what might happen. And I'll show you examples of that. And as far as we know, the kind of physics that we're extracting, well, it's our singularity formation, critical phenomena. I'll give you an illustration of this, nonlinear wave propagation, and more recently turbulence. So these are kind of things that the solutions in a gravitational system might actually develop, and whatever technique one is using better be capable of extracting it. So let's just, if I were kind of thinking from a applied mathematics point of view, saying, well, can my techniques do something in this context to help? I can tell you from the numerical relativity side what are the things that keep us at night, and Deidre and others mentioned these. So with respect to binary black holes, well, we have more or less under control the black hole size is 1. So if comparable masses, that's fine. Modulo things that will happen later on, but I'll make a comment later. But if we're thinking of a black hole of, say, size 1, and another one which has a size of 1,000 times smaller, that's when things are very much demanding for us. So we could definitely do it, but we would like to do that problem for very long times, evolve many cycles, keep the error under control, and make sure we extract all the physics. Some years ago, there were attempts to do some implicit integrations, which will bypass some of the requirements of very small timescales, but that was throwing away some of the important physics that one would like to get in this problem, because they are features of the waveforms that are coming out that are commensurate with this size, and you better be able to capture it. So it's not just achieving long-time iterations, but it's achieving them with the accuracy required for the detector that will measure that particular waveform. So the accurate characteristic requirements, and we heard that this before also from Pablo, is say 1 radian over many, many orbits. But eventually we'll have much better detectors. And these will keep getting smaller and smaller as the signal to noise ratio of the detector improves, as the detector's sensitivity gets better. Of course, it can't hurt to have discretization that respects the symmetry of the diffeomorphism constraint. And this, I would say, forget about gravitational waves. This is important regardless of numerics. This is an issue in some approach of quantum gravity. There is some number of people, Bianca Dietrich, a colleague of mine at Perimeter Institute, is very interested in this approach. They want to kind of picture gravity not in a continuous spacetime, but it's in a discrete spacetime, and the diffeomorphism issue is paramount in their buildup of a potential theory of quantum gravity. If you, for whatever reason, just to advertise this work, which may be important, not because it was one of the authors, but it might be important for you, it used to be that we know we have, and we've seen many times, the Lagrangian for general relativity, but if you have boundaries, now you have to worry about what particular extra contributions those boundaries might be requiring with respect to the Lagrangian. We had the boundary term which was introduced by York, but it's known as a Gibbon-Hawkins term, and so I guess we should call it a York-Gibbon-Hawking if we're going to call it that way. But that was a term that was known only if the boundaries were space-like. You might have boundaries that are time-like or null, and so this paper just works for any possible boundary. So if you have a method that requires a Lagrangian, then you know that you could do general relativity with a complete Lagrangian now. So we heard several interesting ideas from the math side that actually might be quite important. In particular, we heard about symplectic variation in iterators. And Erwan, thanks to Erwan, who pointed this paper to me from Richter and Lubich, which I haven't noticed before. And they had actually implemented some symplectic iteration for the Einstein's equations represented in the ADM form and applied to some very simple settings. It's intriguing that they didn't get anything that was completely obviously wrong. In fact, the results are relatively or rather hopeful. Even though the settings were very simple, it at very least is sufficiently tantalizing that I would like to take a further closer look to it. Thanks, everyone, for pointing this to me. We heard about the finite element exterior calculus, and especially for the Einstein-Bianchi, it looks tantalizing. The Sorkin toy model seems to be something that it's an interesting first challenge to go after it. I would, if I were to think about this, it seems like an obviously ideal problem to mentor a student, and I might try and do that, in combination with the above. So let me start with my first toy models, and I go through a whole bunch of them. Suppose you're going to tell me your technique is going to be useful for representing this very large difference in scales, and maybe also to be able to do very long time iterations that are faithful to the solution. I would like to see it apply first in a simpler problem, and this would be one. So take the box of phi, and this box could be with respect to any metric that you want. For instance, it could be the flat metric, or you can throw a Schwarzschild black hole or a curved black hole to have something where energy gets lost into some hole in your space-time and to infinity if you represent the boundary in any particular way. And you can imagine there's our two sources. I put one source here and the other source in the other side, and let's just make the source rotate by hand. I put two Gaussians with scales L in this one, little l in that one, and of course I can make this little l scale in some way with respect to the large L. I can make each source have its own kind of wobbling frequency. I'm calling omega, and I'm going to have this little wobbling frequency be commensurate with the size L, and so I can adjust it this way, and I can have this omega be whatever frequency I want, or I can even make it change both omega and the separation R with some particular law that is representative of the binary black hole problem. So I can put, I know precisely what that power is, though I don't know it from the top of my head. Maybe it's 8, I think. And I can just shrink the source as I get closer and closer over many, many orbits and increase the frequency following Kepler's law, this would be, in my mind, a very good test for any technique that can promise me to deal with this problem. This problem, unfortunately, that one does have no constraints. So we talk about controlling the constraints, or what is the role of constraints in evolutions. So typically we do free evolution schemes where we're talking about non-symmetric problems. If we can reduce unknowns by symmetries, for instance, in the case of spherical symmetry, we can typically use what we call constrained evolution or partially constrained evolution, and the constraints are part of the update of the fields. But if we put that aside and consider staying with the free evolutions, we want to know what happens with the constraints. And typically, we seem to see that regardless of how nice a symmetry properties the formulation we choose might have, constraints seem to want to go to just diverge exponentially. And so an example would be Maxwell, just to take it first. But Maxwell has constraints that stay put. Even if they have some initial violation, analytically, that violation gets preserved. So this is the example that was mentioned in the array. So I just throw in a term. I throw it in from completely out of the blue. But if I analyze this system of equations, it will have an exponential growth of the constraint given by the divergence of that vector b. And the constraints will also advect with the b vector as well. So if one has a scheme that reproduces the analytically expected exponential growth, that would be a good sign in my mind. I can come up with another toy model that's related. So we know we take Maxwell's equations and take another time derivative and replace one field by the other, when we end up having a wave equation for each field. So imagine this equation and throw in for good measure this term. So now I turn into a nonlinear problem. Doug was asking, do you know of a nonlinear problem that has constraints? So I think this is one of the best things I could do that will keep things sufficiently simple that one might think of giving it a try. So if you ask, what is the equation that governs the constraint, the divergence constraint, then I would take the divergence of this. Of course, as I throw this term or that term, if I'm satisfying the constraint, I haven't changed Maxwell's equations. But now if there is an initial small violation, what is going to happen? Well, if I take the divergence of these and work out what the induced evolution equation is for the constraints, this is what I have. So I have the wave equation for the constraint, added with these two terms, a c squared and a b div c. And again, depending on the sign of b, this might grow and then has a nonlinearity here. So I'll be curious to see how things work with that, with this case. Of course, in my mind, the way I would approach it is I will add damping fields, force the constraint to be satisfied, and try to control them that way. And this is what we do generically. And I'll show you an example next. So this is not just a toy model. It's used for doing physics. It's a force-free electrodynamics model of Maxwell's. So if you have Maxwell's equations, and you insist that your current is such that any non-neutral particle in the system were to have no Lorentz force acting on it, you can deduce rather easily that there is a current that has a component along the E cross B, and then this should be J sub B, and another one along B. This comes from requiring that Lorentz force is satisfied, which implies that E and B are orthogonal. And if you take the time derivative of it, you can obtain what this current is, or this contribution to the current is, this factor. The problem with this factor is it's a very nasty factor. It has gradients, and if you analyze the hyperbolicity of the system, it tells you that the system better satisfies this relation, b squared be larger than e squared, so it should be a magnetized situation. Otherwise, things will just not blow up because the system ceases to be hyperbolic. This is a system of equation that is thought to govern cases where you have a plasma, but the inertia of the plasma is irrelevant with respect to the energy content in the electromagnetic fields carried by that plasma. This is being applied to, for instance, the image of the black hole that the EHC has produced, and to try and understand possible electromagnetic counterparts of gravitational wave events. So this is an example. These are the two black holes you've seen many times in this workshop, but now adding to it a source, given by this electromagnetic model and the force free, and then you ask what will the system do, and then you see that as the black holes go around, the plasma reacts and is influenced in such a way that takes a little bit of energy from the rotational motion of the system and puts it in the electromagnetic fields and generates the jets. As the merger happens, then you end up with a single black hole with this jet, and this is known as this case is the Blandford-Snag solution, if you want. So how is this done? Well, there are two ways of doing it. There's a standard way that is done in astrophysics, and this, just to show you something that you're familiar with, is E with two E's. That should be another E here. In astrophysics, this is known as a Hawley-Evans algorithm, where the electric field and the magnetic field are staggered with respect to each other. So this is what people do. There is something else that you add to just control what happens when B happens to be 0, which is exactly very close to the black hole, say on the equatorial region. So there you put in by hand a little bit of shaving off energy. You shave energy from the electric field, which represents physically the energy that went into charged particles that get accelerated and have something to do with the jet. The problem can be done in a Boltzmann distribution in particles in cell codes, but this is extremely expensive to do all this. So this effective description is very able to capture what is going on in the large scales. And when compared with what particle in cell codes are showing, there is quite good agreement. So this is where people work with. But I'll show you, I'll show you some examples later. But you've seen or you've heard that we have to use adaptive mesh refinement, that we create grid points with discard when it's not needed. So in this kind of scheme, the Yi scheme, where a grid point for H kind of is in the center of the cell that describes E, if you now were to introduce adaptivity, and at some point you need to refine, that thing that my algorithm wants me to have at the center of a box, all of a sudden is at a vertex. And so you have to kind of reflux that, redistribute this into the new cells, or in the center of the new cells that get created. And a lot of the nice properties of the Yi method get thrown away, or get recovered in very particular cases, constraining the type of order of the method you are using. The flip side of that is kind of what we did here, which was to use constraint damping and be done with it. So we just evolved. If I want to change my code from 4th order accuracy to 8th order accuracy, I change one parameter. It picks a different order of derivative operators, and I'm done. Following also Doug's request, he was, well, is there also a model for nonlinear electrodynamics everyone can think of? There is this model called the Born-Infeld model, something that David Garfinkel mentioned to me some years ago, which was introduced to essentially regularize the infinite self-energy that the charged particles would have. And so in this model, the Lagrangian is given by this. If read it in terms of the electromagnetic field, this is what you have. The constraints, unfortunately, are still linear in the unknowns, but the equation of motions get significantly complicated, and so this would be another interesting model. I have no experience working with this model, but that's another interesting possibility to work with. And then I said, well, we also need to be on the lookout. So this is as far as how maybe some toy models that would challenge our notions or our ability to represent multiscales with respect to distribution, size, the sizes of sources, length scales of simulations. But also we should be on the lookout for possible things that we couldn't possibly imagine the solution will develop without having seen it first. As I said before, GR is such a rich theory of which we know quite a bit from global arguments, from geometrical arguments. But with respect to possible solutions, I think we're still scratching the tip of the iceberg, and I'll show you a couple of examples. Both examples were obtained and were numerically, and they were instrumental in understanding new phenomena that otherwise we wouldn't have had. To me, the quintessential applications of numerical relativity and general relativity still is this work that Matt Choptrick did in 1986, which led him to the discovery of critical phenomena. So imagine a following problem. Take a distribution of just a scalar field. This is providing some energy content in your space-time. And let it implode. So what's going to happen? Well, this scalar field will go into the origin, will just, if it's not sufficiently gravitating, it will kind of bounce off the origin, go to infinity, or just cross each other to be dispersed away and never to come back. You also think, well, if I put a lot more energy in my initial condition, as they go towards the origin, they might form a black hole. So there's a clear separation of two possible end states. A black hole on one end, flat space in the other one. And then you say, what the hell happened right at the verge of black hole formation? Let me show you an example. This is a movie by France. This is a scalar field. Infinity is that way. And for visual impact, even though this spherical symmetry, he's added kind of one of the angles, and so as to see the movie in a much more interesting way. You're going to see the time. This is the scalar field. This is right below the critical parameter that will give you a black hole. I'll tell you what that black hole is in a second. The scalar field goes in, and as it gets closer and closer to the origin, its self-gravity begins to do something very interesting. You're going to see some features of the scalar field, and then we're going to slow down time. So this is in log time and log scale. And you're going to see the space-time repeating itself in a very interesting fashion. So anyone that sees this and tells me that that's what they expected, I think that that's lying. Better yet, you can ask what happens with, say, curvature invariance or the mass of the black hole that you form as in the way it depends with respect to the initial perturbation size once you get close and close to criticality. And lo and behold, there is a particular law which is universal. It doesn't care as long as you're in this with respect to the same physical description of the problem. The parameter is universal. It didn't care what the initial profile was. The critical value might be different, but that slope is unique. There might be a self-similarity, which could be discrete or continuous, and that gives you an R parameter, which is also universal. Who in the world ordered that? Where did these numbers come from? We have no idea, but it was a simulation that got that out. So this is in the context of asymptotically flat spacetime. Either the scalar field form a black hole or disperse away, and right at the verge, it formed a black hole of zero mass. So it's a naked singularity, which is essentially the silliest singularity it might be, yet it's a singularity. All the curvatures blow up, and the future of the black hole, of that naked singularity, this gravity has not, general relativity has nothing to say because it has lost predictability. This critical phenomena has been showing up left and right in the field whenever you try to fine-tune between two different possibilities. A very interesting work, and this is also something that Pau alluded to, was by Bison and Rosorowski, where they said, well, let's just put the same problem, Chadwick problem, but in anti-de Sitter. So anti-de Sitter is a fancy thing. If you don't know what I'm talking about, just imagine putting gravity with an extra potential that just diverges at large distances. So it diverges in such a way that if I were to throw a ball with whatever strength you can imagine, even if it were going to with the speed of light, it will eventually come back to me and hit me at a finite time. So for all intents and purposes, imagine just it's a box. So they do that, and they do exactly the same thing as Choptic. They say, well, just put initial condition with some given parameter. Does it form a black hole? So this object can go and form a black hole right away. The energy goes to infinity, but then it has a chance to come back. And then maybe it bounces a few times, and eventually it always forms a black hole. You might have to wait 123 different bounces of this object going in and out, in and out, in and out. But all along, the energy content that it has is slowly shifted to higher and higher frequency. There is a weakly turbulence behavior of gravity that is taking this field for the ride into higher and higher modes in frequency space. So that was great. We said, well, this phenomena shows up. Gravity can generically form a black hole with arbitrarily small amount of energy if you confine it. Then we looked at that problem again, and it turns out that, well, that's not so easy. There might be configurations that do that eventually always form a black hole, and there are others that at some point they just decided to not form a black hole anymore. So now it's a very active field of research to try and understand how generic the initial conditions are that form a black hole and those that avoid the black hole, and then trying to understand what happens at the very, very limit of just trying to perturb this space-time that is essentially flat if it weren't for this extra potential that is added in. The interesting thing of that is to just point to another simple model that was introduced by, I can't remember who introduced it, so that's my bad. Where imagine this Lagrangian, which is a standard Lagrangian for a scalar field, but throw in for a good measure this phi to the fourth potential. You can do it in ADS, or you can do it in flat space-time. Just put flat space-time, put some reflecting boundary conditions there, and by and large, much of that the phenomenology that these two simulations are showing is captured by that model. Eventually, there are differences. But if you do that problem with whatever method you like, I'll believe you could do this. Or I'll believe one of us will adopt your model, your approach. So another surprise that also came from the ADS front is that generativity can go turbulent. It used to be that people would say, no, generativity is a theory that has no shocks, and that's a very typical hydrodynamic phenomena. It's very unlikely that generativity will have turbulence associated to it. But in the context of this ADS-CFT conjecture, which, again, doesn't matter what it is, in the context of asymptotically anti-de Sitter space-time, so where you have this infinite potential, you can decide to project the Einstein equations onto that boundary at infinity, which, again, is in causal contact with you. And if you assume a gradient expansion, i.e., the fields are sufficiently smooth that higher derivatives are subleading with respect to lower derivatives, lo and behold, you recover that you can write Einstein's equations in terms of relativistic viscous hydrodynamics. You ask what type of phenomenology you will have here, and it's indeed the phenomenology above a sufficiently high Reynolds number. And so you expect turbulence to happen. And I will dare you to say which one was a generativity simulation and which one was a hydrodynamic simulation using the dictionary that links the connection between Einstein's equations and relativistic viscous hydrodynamics. If you want to guess, it's not this one. So the funny thing is that people that work on the field theory side decided to do the simulation, the generativity simulation. People that work on generativity decide to do the hydro simulation. And we get very consistent results. And I should put a side note here. This simulation is done in the formulation of generativity, which is called the characteristic formulation. This rides on null hypersurfaces. So it's funny if you ask people in the string theory side, what is the most used numerical technique, numerical formulation for doing generativity in anti-de Sitter, they will tell you it's the characteristic formulation. Many of them have never even seen the Cauchy problem. And you get the exact opposite answer if you ask on the binary black hole problem side, on the gravitational wave side. So it's interesting that there are many formulations in generativity, and there are some that are better for a particular problem than others. So one interesting side effect of that connection is now you can choose to do gravitational dynamics and use the result to shed new light on hydrodynamic problems, or you can use hydrodynamic intuition to point to new opportunities in gravity. In fact, going and digging out that gravity can go turbulent was in that way. Was first in understanding, we understood, oh, wait a minute, if this applies, hydro should go turbulent. In fact, my initial reaction was, I'm going to show these string theories that are all wrong. And it turns out that I was the one that was wrong. Gravity does go turbulent. So this is an example that we've seen before with respect to how you could encode a surface that is S2, and this is something that Lee talked about, where we're going in that direction. I'll tell you why. So here is the vorticity of a given fluid. This is a relativistic fluid with a particular equation of state. It doesn't matter the details. And then we're going to see how this evolves. And again, I can dare you to find where these patches, these multiple patches that Lee was describing, exist in that grid. We're using, again, finite difference operators that respect summation by parts. Boundaries are treated with the penalty method that penalize whatever mismatch in between the value that comes from one side and the other one, and we drive that to satisfaction. This is using a code that was initially developed by Oscar Reula. And let me just show you the movie. This is, as I said, it's in the turbulent regime, so after a while, this thing will go crazy. We generate all these vortices. were in 2 dimensions, so vortices that have equal sign want to join. 2-dimensional hydrodynamics is interesting in that it wants to cascade energy primarily to longer wavelengths as opposed to short wavelengths, and this is represented here. But recently, we got interested in a similar problem, just because if you look at Jupiter, they have this vortices structure near the poles, which they call the crystal vortex. And Western Nacher Schneider, the same person that Harris was talking about, and Federico Carrasco, a postdoc in Germany. When he was my student, Federico was Oscar's student, working on this very interesting problem that you could say, can there be a situation where turbulence eventually take you into something that shows multiple vortices that even though they are rotating in the same direction, and they should be approaching each other and trying to merge into a single one, they don't, and they just stay for a very long time there. That's an interesting problem in both in geophysics and also some other fields in fluid dynamics. What's it? Oh, great. I'm going to tell you. Have you seen the movie Sharknado? You shouldn't. So what this is from at the boundary of ADS, you have this vortex. What the dictionary tells you is how that vortex gets impact in the rest of the space-time. So what you have is almost a realization of what Wheeler used to call a geon. So it's a quote-unquote self-gravitating concentration of gravitational waves that are sufficiently strong in their self-gravity to not disperse immediately, but there is sufficient rotation to not have them want to collapse. And so you have this thing that extends from the boundary all the way to the interior black hole. Thanks for that question. Also, the viscosity of the problem, what is the viscosity of the problem, is low, and is given in the gravitational language by the energy that gets lost inside the black hole, and the viscosity parameter is just some natural number, 1/4 pi. And so what we're trying to do now is just use now gravitational intuition to try and explain the existence of these vortices, which is a topic of debate nowadays. Okay, let me just now really throw in serious matter. We're going to something like Harris was talking about. Let's imagine that one of the black holes is a neutron star, or both are neutron stars. So what do we do there? David was saying, oh, it'd be interesting to tell them a little bit what we do in the other problem. So I'll tell you a little bit on completing or adding to what Harris has said. So we describe matter by relativistic magnetized fluid. And I would say there are 3 problems that one could imagine doing here. There's a problem we should be doing. That's the problem that nature wants us to solve, if we're going to be representing it. There is a problem that we can be doing, which is the one where we have control of the physics in a way that we can put in a computer and do in a reasonable amount of time. And there are toy problems, but those might not be sufficiently rich to really tell us something that we can use LIGO to go dig for interesting clues as to the behavior of nature. So this is a very interesting case where we actually make some compromises. And so it's not so easy to say, oh, can I use maybe a Hamiltonian formulation of hydrodynamics? So, well, because there are other ingredients, and I'll tell you some of those, and that complicates the purest form. So we want relativistic magnetic fluid. The equation of state, well, would be pressure depending on temperature, density, as usual, but also composition. We want to know what that fluid is made of and what particular nuclear processes might actually turn on to produce neutrinos and take energy away from the system. And that could be crucial, not when the spiral is happening, but after the merger took place. So we need to account for nuclear processes, for instance, in particular neutrino production, the emission, the heating, and the transport of energy and momenta by neutrinos, which could be huge. We have multiple instabilities, in particular magnetic ones. Winding is an easy one. Winding has the scale of the neutron star to act. We have Kelvin-Hamilton instability. Well, that's a scale divided by 10. These two are well captured in current simulation. But the MRI is like the size of the star divided by 1,000. So that's still very far from reach. If anyone has an idea of how to do this, that would be amazing. There are people trying to do subgrid models, and these are very good efforts where they actually capture the physics in the right way, that's a different question. And then we also need long times. So it's not the story, the movie doesn't end when the black holes collide, as in the case of black holes. The movie keeps going for black hole, neutron star, or binary neutron star, because the object might form promptly a black hole, in which case it is like the binary black hole problem. But if the object is a neutron star that hangs in for a while, there is very rich information on that gravitation that is going out. It might take for a short time or very long time to collapse, if at all. And so you need to understand all that and be sure to incorporate the right physics that is really making a decision of what is going to happen with this object. So the physics involves describing the tail, the disk that might be produced, the disruption of the object, the amount of ejected material. One of the main signals that was obtained after the merger of the purported two neutron stars by LIGO 2 years ago is this kilonova. And that's this ejecting material, which is very low density material flung out from the system, and you need to capture that. And then you encounter problems like Harris was saying, the atmosphere is very crucial there, and then the neutrino and electromagnetic counterparts. So I dig out some very old movies because of one of the comments that Doug was making to me. Oh, holes being represented in finite difference are very, very unnatural. You have something that is smooth, and then how you do that? Well, LIGO sphere is ugly, and indeed, it's very ugly. But if the spin is not too high, you can just have a cube. And the cube, as long as the cube sits inside the black hole, it's relatively easy to put the right the deformations of your finite difference operators to account for that hole. So I'll show you this movie that was, this is like 10 years ago. The black hole is accreting from a neutron, encountered with a neutron star. So it's going to disrupt the star, and it's going to start eating its material. All along, it was very crucial in this problem to have this regrading be self-aware of what the features of the solution are, because you're eating some of the material, you're disrupting the star, there's a tail that is coming out, and you need to resolve, or you like to resolve all of that physics as much as well as possible. So this is a snapshot at some intermediate time, and this kind of, it's not a cube anymore. Well, it's a deformed cube. It's a prism, whatever, what's the right word? I don't know. So you have not an equal size cube that is adapting as the dynamics goes on. Now we have a different problem, because I also wanted to say not everything is a binary black hole problem, but let me just show you a black hole problem acting in a very weird way. So this is recent work done primarily by Will East at Perimeter Institute. This is black hole as endoparasites. So if you think of the context of either primordial black holes or dark matter that can accumulate at the centers at the cores of neutron stars, they can conglomerate at the center and get to be dense enough to form a black hole. So you're forming a tiny, tiny black hole. It's a size of 1 billion times smaller than the size of a neutron star. So how in the world, that cannot, there's so many different, such a large different scales that we cannot do that. So the best we could afford nowadays is to think, well, the black hole grew to a size of about 100th of the neutron stars. So we're doing pointing a very tiny black hole at the center of the neutron star, and then seeing what happens afterwards. This is a neutron star that has a rather kind of mild rotation, and this is one that is rotating almost at its highest possible rotation. And the question is, what happens with this? One option that has been suggested before is that as the black hole grows, angular momentum transport takes rotation from the core and keeps pushing it outwards. And at some point, it has pushed enough that then you disrupt the outer layers of the star. You throw a whole bunch of material outside. And this could go through the same nuclear reactions that will generate the signals like eventually like a kilonova. So people have put out as this silent kilonova possible mechanism. So the work that we did with Will, again, but it's primarily Will's work, was to try and answer that question. So here you see that this is zooming in and expanded by 64 times. The black holes are growing and growing. And eventually, well, you see what the answer will be. By the way, an endoparasite, I found that word when I was looking at what is the beast that is in the movie Alien. And then it turns out that it's a proper name because the black hole will grow and eat up the whole star in both cases. Nothing really gets ejected. And the black hole acquires many of the properties of the host. as the little thing that was threatening Sigourney Weaver in the movie. Okay, so I'm trying to wrap up, I think. So some interesting points, at least from that I'm taking home. I like to take a closer look at these symplectic methods and see how much one can go. I mean, the promise is very interesting that it can do many, many, many orbits under control. I'm worrying that the problem we're trying to solve is one that we have the long time requirement, but we also need the accuracy. Will it be able to do that? I don't know. In contrast, that's a misspelling, sorry, with the Newtonian problem, the problem where this would seem to be very well suited for is a self-force problem of an object inspiring around the supermassive black hole, but there you have to deal with the regularization of the self-force and the radiation that is going out, and ultimately that's the signal. So we don't really care if Jupiter goes around the sun a million times if we cannot capture the very weak gravitational wave that Jupiter and the sun are producing as this happens. The symmetry preserving schemes sounds, at the very least, if I could implement them without any further cost, I would definitely be doing right now. And I'd like to understand how good the properties are in preserving constraints or gauges. And of course, there are examples that I gave, the Maxwell in terms of E and B, or A and phi. So here we wouldn't have to worry about gauges, but how well is it to preserve some particular gauge that we might have chosen here? And it's interesting. I would like to understand more both Fick and Deck. And always, as my little Lego man at the very beginning of the very first slide, we are always looking for flexibility. We're not only thinking what we're doing now, what else we want to put in that code, because we know the physics is richer than we're always doing in some ways. I am interested in high convergence order. Binary black holes code are very, very efficient nowadays. When you ask how many processors you use for that, a few hundreds, a few weeks, and then we're done. And it's interesting, we're fighting with super computer centers for getting time, because they say, no, we paid, or taxpayers paid, for a computer that has hundreds of thousands of cores. We want you to use them. And they say, well, but I already work and make my code efficient. Oh no, but if you're not running with more than 200, more than 1,000, we really don't like your proposal. I think that's a really stupid argument. As a taxpayer, I really don't like it, and I would wish everyone pushes back on that silly, idiotic argument. You can see I have an opinion on this. As final words and discussion, this is something Pablo already did say. At its heart, any code, whatever code, is obsolete the moment it's done, or the moment one starts using it, because you develop for the current architecture, and architecture keeps improving. Not only that, it gets worse with time, because it gets old, and we keep adding physics. So most of the codes that are out there are of the order of 2 decades old. They are very, very old. They are better newer versions, like G.R. Chombo, Simfloni, but it's still true. They are already old by the time they came out. So eventually, we always want to hear better ideas, and if we can implement them easily, we will try. What are the main goals of our gravitational waves, especially in the binary black holes? We're asking ourselves what methods can expedite the solution to scan for new regimes, especially in the higher mass ratio and higher spins. I also want to stress there is a difference between discovery and accurate description. A discovery, I want to get the answer to the first significant digit. Accurate, I want much more than that. And in fact, nowadays, there are both types of code. There are codes that are getting the first physics out. They are not very accurate. And there is another one that is much more accurate. It's the one that is used at the practical level in the LIGO-Virgo collaboration a lot more closely. But then it depends where you want and what side of that equation you want to be. You want to be the one that finds a new phenomena, or you want to be the one that got the solution that was used for the detection. I'd rather be on the first case, not necessarily, I'm not that interested in the second, but that is very, very important, and there are lots of people working on that side. So you can try to go here or try to go there. There will be different tastes to take your ideas. But sooner or later, we're going to have to all face this problem. How can we go to achieving higher accuracy better detectors are coming online, not too long from now. We know how long it takes to get to the right place today. We're worried about whether we're going to be there for things like LISA or third-generation detectors because their signal-to-noise ratio will be much, much higher. So it is safe to say that nothing we're doing today carries over for even a decade from now. I keep stressing the point that I think I want, at least from my personal view, as methods that are flexible to grow in physics. And then for black hole neutron stars and neutron star binaries, we're in a much lower, in a much weaker position. Accuracy and time to solution are already an issue, as opposed to a few hundred process or 100 in a few weeks. We're talking about 300 cores in 2-3 months to do a rough calculation. And we know that the amount of physics that we're going to be adding cries for flexibility. So, and the last point I wanted to make is just you hear a lot about binary black holes and general relativity and numerical relativity. That's absolutely true. It's the area that is used the most. It's the area that, in some sense, is very relevant because of the times we're living. But there is a lot more life in general relativity than just gravitational waves. We must be ready for surprises. And who knows, just your application, even though might have nothing to, your ideas might have nothing to do with it, with these fronts, they might be useful for others. And GR is quite rich in problems. So I'm going to stop here. Thank you. LIGO to claim detection is order 10, let's say. So so LISA will be, yeah, LIGO in the best cases of the order 30, 40, unless if a signal is very, very close, okay, it could give you 1,000 if it is next door. But the typical source is sitting around 10, 20, 30s of that order. Well, LISA will be at 1,000, and the 3G detectors will be an order of magnitude better in, so it would be, what is it? Well, I won't be able to do this on my feet, but so LISA, the 3G detectors will be good to see black holes at the edge of the universe. So any black hole that has ever emerged in the solar mass range, in the 10 to 100 solar mass range, LISA will see them all. We will see LISA, sorry, the 3G detectors. And binary stars will essentially see all of them as well because they get formed later. Their signal is weaker, but they get formed later.
And the ones that we're detecting now with the waveforms is very different.
So the ones we would see them with LISA, but LISA, the ability to have an SNR that is 1,000 allows you to probe, and this is something that Franz was saying, allows you to probe to some physical phenomena that is deeply weak in some sense in the effect on the gravitational waves that LIGO is not allowing you to see. So one example is the black holes that merge, you ask, and then you saw the gravitational wave just decaying and then going to quiescent because it just formed supposedly a curved black hole. People have been able to identify the main quasi-normal mode, and there are arguments that maybe there is another one, but just one. That was extremely close, extremely loud, and you couldn't dig it out. You couldn't dig out the further modes. Digging out the further modes allow you to put a very stringent test of general relativity. For binary neutron stars, Harris was showing how it constrained the radius of the neutron star, but that's because there was a lack of feature. But in between, in the window that he showed, okay, these are equation states, you like to tell the difference between this, the effect of this equation state of that and that one. And LIGO is not going to give you a good answer to that unless you have hundreds of events and you combine them in a particular way to dig that out statistically. But to see it in each individual event, that's what this higher SNR will allow you to do. So Helvi had a...
So it's going to have this
Right, perhaps another figure of merit. So another figure of merit is the test that LIGO has done with GR gives you GR to within 10%. That's a far cry for how well we would like to constrain the theory. And then you always, well, in a scenario of 1,000, we'll bring that 10% to by a factor of 100 down, or 50. So let's see. So I think the answer is absolutely. It would be great that you could do that. I'll tell you one thing that you might have to be very worried about. I would say today, we are not seeing any problem. We can do this with the right method. People that have done it using the kind of a Y method, again, they don't have any problem. But some of the problems they're dealing with, so the problem they have dealt with the Y method, or the analog Y method, is that of a pulsar. Imagine you have a star, and now forget about the star. Imagine you only have the boundary, and then you solve the problem in the outside of it. So there's a beautiful work by Anatoly Spikovsky who cracked the problem of what is the solution of force-free electrodynamics outside of a rotating star. And that's key to understand how pulsars radiate, which even 50 years after the discovery, it's a question mark. So here, they have done it. But of course, once you set that the grid, whatever grid it is, and they have conform, because you have a sphere, the star is a sphere, and then they have conforming grids, radial grids there. So they don't have to deal with the origin, and they just need the outside. So in reality, in that problem, they never had to worry about adaptivity. Now imagine you want to collide this with an R1. I don't know how you're going to do it with Y in a simple manner, but I'll be happy to see it done. So that would be an example. One thing that you have to be careful, and I don't know how you would deal with it, and then the good thing about finite difference in my mind is, and it's both its problem and its beauty, is that it's very permissive. So it allows you to think you're doing well for a while, even though you could be doing horribly, and then you have to do the convergence analysis and all that. But one problem here is that suppose you have this field line that is going out. Now this is rotating, the space-time is rotating. So what you end up doing is a magnetic field, if I were to look from above, oh no, just from here, let's say, you end up having a B field line here that gets wrapped around, and then in a sense come back from the other side. So it changes sign. When it changes signs, then there is a zero in the middle. Because there is a zero in the middle, well, the first thing is you violate this condition. And then, physicists, we have ways to give names to anything. So what happens in the middle is it's a current sheet, which is, again, it's like dark matter. It's just an excuse for something we're not controlling, nor we know what it's doing, and we're just going to do something with it. And this is where you say, well, if E is getting to be larger than B, and at that point it is, you're going to shave it off. So you just take it E, and then you bring it to zero by hand. So what you're doing is just taking energy away from the system, and you imagine there's a physical consequence. I don't know how you would do with it, but I imagine you're going to have to deal with the same problem because the formulation has that problem. It might be a very natural, in your case, to do it, a natural way, and that would be very interesting to see. But there are lots of problems in force-free electrodynamics that one could do, and yeah, I'd be curious to see what the answer would be.
So this connection to gravity and 2D hydrodynamics, is it only to spheres, or are
thank you. I should have, I went too fast. No, the connection is between D plus 1 dimensional hydrodynamics and D plus 1 generativity. So generativity gives you, or gravity gives you the extra dimension. So this is not a sphere, I should have said it. There is a way to take ADS and by a conformal transformation and wrap it in some ways. So now your boundary is flat. So this is in a flat boundary. So you can do hydrodynamics over a flat space-time. And the beauty is that it's identically flat. So you don't have to worry about the gravitational part. Or d plus 1 hydrodynamics on a sphere. Those are the two easiest applications. And you can do one or the other one, that's fine. And this would be good. You have your hydrocode, you get the solution for that regime, and then you follow a very simple dictionary, and you say the metric in the spacetime is that, and you haven't solved Einstein's equations. In fact, the argument is you solve it without knowing it. In this regime of large gradient expansion. What's what? Oh, right. So the motivation is more than one motivation, and then you can poke holes on it in more than one way, but it's like whack-a-mole. One interesting will come out at the end. So there is a motivation. So it doesn't have to be the primary black holes are not that small. Primary black holes that would have radiated away through Hawking radiation and be irrelevant. So they are slightly larger. How do they come about? Well, it could be part of dark matter, or it could be in themselves, the black holes be part of dark matter, or the dark matter could be just described by some bosonic field that, because neutron stars are so much more gravitating than other things, end up slowly accumulating in the center. You go above the Hooke conjecture, and then you form a black hole. And the one side motivation from astronomy is that there is a famous missing pulsar problem. So the center of galaxy, our galaxy should have many, many pulsars, and we only know one magnetar. So where are they? So well, you say, well, maybe there is something that is killing them. This argument can only go too far, but okay, that's an interesting. That's one interesting idea.